Please come to the chapter 1, that is types of switches. From this, the concepts are important for any competitive point of view. Already so many times the questions are framed in GATE, IES, in other competitives based on this concept. In this chapter 1, types of switches concept, first we'll see what are the different types of switches are available. In general, this is a general classification of switches. In general, switches are classified into two types. The general classification of switches, that is, in general, switches are classified into two types. Switches are classified into in general, switches are classified into, one is ideal switch. It's a general classification, ideal switch. Another one is practical switch. One is ideal switch, another one is practical switch. Yes. Now see, what are the properties of ideal switch and what are the properties of practical switch? This I want to discuss. First we will see what are the properties of ideal switch. The properties of ideal switch. In general, a switch can be represented like this. This is a representation of switch. Let current through the switch is ISW. Voltage across the switch is VSW. What do you mean by operation of switch? The operation of switch is nothing but a switch on, switch off, switch closed, switch open. It is having two states, on state and off state. Now, if the switch is on state, what is the observations? If the switch is off state, what is the observations? One operation is nothing but a one on and one off. One operation of switch is nothing but a one on and one off. Okay. Switch on. Switch on. If the switch is on means this is closed switch. Closed switch. Here I am talking about ideal switch. Ideal. What is the voltage across the switch? 0. If the switch is on condition means it carrying the current. But I am telling that ideal switch now. That's why it carries any current from minus infinity to plus infinity. It carries any current from minus infinity to plus infinity. If the switch is on condition, voltage across the switch is 0, but it carries any current from minus infinity to plus infinity. If the switch is on condition, whatever the losses takes place in a switch, those losses are called conduction losses. But it is ideal switch. Voltage 0, but current is exist. Power loss is nothing but a product of voltage and current. but voltage 0, current only exists. Then what is the power loss? 0. Then what is the power loss under switch on condition? Those power losses are called conduction losses. That's why, what are the conduction losses? In ideal switch, conduction losses equal to 0. Conduction losses are 0. But one operation is nothing but a one on and one off. Next, switch off. Switch off means switch open. If the switch is off means this is equivalent. This is the voltage across the switch. If the switch is off state, what is the current through the switch? Then what is the voltage across the switch? It is ideal switch now. It blocks any voltage from minus infinity to plus infinity. If the switch is off state, whatever the losses takes place in a switch, those losses are called blocking losses. But it is ideal switch now. Current is 0, but only voltage is exists. Product of voltage and current 0. That's why. What is the blocking losses? Blocking losses are 0. Blocking losses equal to 0. Blocking losses equal to 0. Then, in ideal switch, conduction losses are 0. Blocking losses also 0. In any switch, there existed 3 types of losses. One is conduction losses, blocking losses. There is another type of losses, those are called switching losses. In ideal switch, switching losses also 0. In ideal switch, switching losses also 0. Switching losses are 0. Switching losses are 0. How to say that in ideal switch, switching losses are 0? Because there is a instantaneous switching from on state to off state and off state to on state. That's the reason why in ideal switch, switching losses are 0. Let this is ISW and this is VSW. If the switch is on state, current is exist, but voltage is 0. If the switch is off state, current is 0, but voltage is exist. Again, switch is on state, current is exist, but voltage falls to 0. That's why this is switch on condition. And this is switch off condition. Again, there is a switch on condition. From on state to off state and off state to on state, there is instantaneous switching from on to off and off to on. Hence, switching losses are 0. But practically it is not possible. That we will see practical characteristics also. Okay, that's why. Why the switching losses are 0 means switching losses are 0 because there is instantaneous switching. There is instantaneous switching from on to off and off to on state to off state and off state to on state. That's the reason why switching losses are 0. Then what is the total power loss? The total power loss equal to conduction losses plus blocking losses plus switching losses. Then total power loss equal to 0. If the total power loss equal to 0, what is the temperature rise? Temperature rise equal to 0. Then No need of cooling requirements. No need of cooling requirements. No need of cooling requirements. Now, these are the properties of ideal switch. Switch is on condition. This is the property. Switch off condition. This is the property. Because of instantaneous switching, switching losses are 0. Then total power loss equal to 0. Temperature rise is 0. No need of cooling requirements. Now I want to represent all these properties in one characteristics. That is, all these properties I want to represent using characteristics. Can you draw this characteristics of ideal switch? IV characteristics of ideal switch. That this is ISW, this is VSW, this is minus VSW, and this is minus ISW. Then how to draw the ideal characteristics of any switch means, this is the concept you follow. Switch on condition. What are the observations? Represent those observations. Switch off condition. What are the observations? Represent those observations. Then you can get the characteristics of any ideal switch, or ideal characteristics of any switch. Now tell me, if the switch on condition voltage is 0, but it allows any current from minus infinity to plus infinity. Yes. If the switch on condition voltage is 0, it allows any current from minus infinity to plus infinity. If the switch is off state, current is 0, it blocks any voltage from minus infinity to plus infinity. Current is 0, it blocks any voltage from minus infinity to plus infinity. This is the characteristics of ideal switch. Understood? This is what exactly ideal switch properties and what are the characteristics of ideal switch. Yes. Note down all these points, very important. Now we'll see what exactly practical switch. I want to discuss what are the properties of practical switch. Types of switch concept. This concept I am discussing. Discrimination. Now see what exactly practical switch. Practical switch. Yes. Yes. Let us consider. Here I am drawing practical characteristics generally. This is a practical characteristics of a switch. Yes. Parallelly draw this figure. Yes. Let this is I, this is V, this ISW, current through the switch, VSW, voltage across the switch. This characteristics of practical characteristics of a switch. Maybe any switch, but generally I am giving these characteristics. Here current is rising, voltage is falling. Then this indicates that this is on state. Voltage is falling, current is falling, current is falling, voltage is rising. Then this state indicates off state. Here switch is conducting. Here a switch is blocking. This is blocking. Yes. This is on state and this is off state. There is no instantaneous switching from on state to off state. Yes, sir. Current is slowly rising, voltage is slowly falling. Here also, current is slowly falling, voltage is slowly rising. That's why during on and off, both during on state, both voltages exist, current is exist and voltage is exist. During turn off of switch also, both current is exist, voltage also exist. In this region, on state switching losses are exist. On state switching losses are takes place. On state switching losses. During this time, off state switching losses are exist. Off state switching losses are exist. Off state switching losses are exist. And during this time, conduction losses are exist. Conduction losses are exist. During this time, conduction losses are exist. And during this time, blocking losses are exist. Blocking losses are exist. Therefore, in a practical switch or it is a real switch. It is a real switch. Practical switch is also called a real switch. In a practical switch, conduction losses are not equal to 0 because during the conduction state, both current is exist, voltage is also exist. This is some leakage current. This is current. This is some forward voltage drop. Small forward voltage drop. During off state, voltage is exist and current is also exist. This dotted line. This is small leakage current. That's why blocking losses not equal to 0. And there is no instantaneous switching in on state and off state. That's why switching losses not equal to 0. Conduction losses not equal to 0. Blocking losses not equal to 0. Switching losses not equal to 0. Then what is the total power loss? Total power loss equal to conduction losses plus blocking losses plus switching losses. Then what is the total power loss is not equal to 0. If the total power loss is not equal to 0, then what is the temperature rise? Temperature rise is not equal to 0. Understand? That's why in a practical switch, temperature rise is not equal to 0. But point to remember, during the operation of a switch or device, every device is used as a switch. Understood? During the operation of a switch or device, if the temperature rise is not equal to 0, it must be operate within the safe operating area. Otherwise, because of high temperature rise, the device may be permanently damaged. Temperature rise causes permanent damage of the device. What do you mean by permanent damage? You don't repair again. That's why practically, to protect the device from high temperature rise, it must be operated in safe operating area or safe operating region. Therefore, practically, to protect the device from, or switch, from high temperature rise, it must be operated in safe operating area or safe operating region. It must be operated in safe operating area, safe operating region. In general, a safe operating area or safe operating region are represented like this. This is a general representation. Okay. But this safe operating area or safe operating region changes from device to device. SCR is having its own safe operating area, BJT is having its own safe operating area, MOSFET is having its own safe operating area. Later on I will give what the safe operating area or safe operating region for different devices, what that area indicates for different regions. Okay, later on we will see. But in general, this is a representation of safe operating area or safe operating region. This is SOA or SOR. Okay. Like this is voltage across the switch and this is the current through the switch. To protect the device from high temperature rise, it must be operated within this area only. But I am not representing safe operating area like this. Like this I am not representing. Okay. This is the safe operating. It is not the safe operating area. See, why I am representing like this means, for example, let us consider a diode, a 100 volts, 10 ampere diode. What is the meaning of this rating? What is the meaning of 100 volts 10 ampere means? A 100 volts 10 ampere diode means, it is not the meaning. If the voltage across the diode is 100 volts, then the current through the diode is 10 ampere. That is not the meaning. At the time of voltage across the diode is 100 volts, current is 10 ampere, then what is the power loss? 1000 watts, high temperature rise, diode may be permanently damaged. That is meaningless. Then what is the meaning of 100 volts 10 ampere? If the diode is under reverse bias condition, it blocks the voltage of 100 volts. In that case, current is not 10 amperes. Current is leakage current, very small current. If the diode is under forward bias condition, it carrying the current of, it allowing the current of 10 ampere. At that condition, voltage across the diode is not 100 volts. That is a forward voltage drop. Okay, that is the meaning of 100 volts 10 ampere. That's the reason why I am representing safe operating area like this. If the diode is carrying the current of 10 ampere, corresponding to 10 ampere, voltage is not 100 volts. Corresponding to 10 ampere, voltage is, that is the forward voltage drop. If the diode blocking the 100 volts, current is not 10 ampere, corresponding to 100 volts, the current through the diode is very small current, that is the leakage current. But if the diode current is 10 ampere, if the voltage is 100 volts, 100 into 10, 1000 watts, then this is meaningless. We cannot represent safe operating area like this. Then this is the safe operating area, safe operating region. Understood? Okay. This is the properties of practical switch. Okay. This is that means in a practical switch, conduction losses are not zero, blocking losses are not zero, switching losses are not zero, then power loss is not equal to zero. When the power loss is not equal to zero, then temperature rise is not equal to zero. If the temperature rise is not equal to zero, during the operation, practically, to protect the device from high temperature rise, it must be operated in safe operating area or safe operating region. Otherwise, the device or switch may be permanently damaged. Okay, these are the points you remember. Okay. Then, how to calculate the switching power loss, how to calculate the conduction power loss, all these later on we will see. Understood? Okay. This what exactly ideal switch and practical. This is a general classification. This is general classification of switches. Okay. But in power electronics, the switches are classified into different types. This is a general classification. But in power electronics, now we'll see. Think you note down this one now. Parallel I told already. Note down. Is completed. Yes. Now we'll see. In power electronics, the switches are classified into different types. In power electronics, the switches are classified into different types. In power electronics, switches are classified into different types. The switches are classified into following types. Switches are classified into following types. Under that, first one is first classification of switches. First classification. This is the first classification of switches. Yes. Then what the first classification of switches in power electronics is? One is uncontrolled switch. The next one is semi-controlled switch. Fully controlled switch. Now see, what exactly uncontrolled switch? And what are the examples of uncontrolled switch? Yes, let us consider a diode circuit. connected with some load. Connected with some load. Okay. This is diode circuit. This is anode and this is cathode. We know that if VAK, anode to cathode voltage, is positive, diode is on. If anode to cathode voltage is negative, then diode is off. That means on and off is determined by, or the on and off state of the diode depends on circuit conditions. Up to what time the diode is on? When the diode is on? When the diode is off? All these depends on circuit conditions. It cannot depend any external control signal. That's the reason why it is uncontrolled switch. That is, on and off is not in our hand. Once the diode is connected in a circuit, when the diode is on, when the diode is off, depends on supply condition and load condition. Those are circuit conditions. That's the reason why it is treated as an uncontrolled switch. It is not in our hand. It is not controlled. It is not depends on external control signal. That's why. What do you mean by uncontrolled switch means? What do you mean by uncontrolled switch means? What do you mean by uncontrolled switch means? No doubt. That is on and off. On and off. Depends on circuit conditions. Circuit conditions. Depends on circuit conditions. That's the reason why it is an uncontrolled switch. Then what are the examples of uncontrolled switch? Total diode family is the uncontrolled switch. Total diode family is the uncontrolled switch. Not only PN diode, you take any diode. It may be Zener diode, or it may be tunnel diode, or it may be varactor diode. Any diode you take, all the diode family is the uncontrolled switch. The second one is semi-controlled switch. Semi-controlled switch. Semi-controlled switch. Or half controlled switch. Half controlled switch. Half controlled switch. Semi-controlled switch or half controlled switch. Let us consider a thyristor in a circuit, connected in a particular circuit. This is load. They are giving some supply. This is anode and this is cathode. Yes. If anode to cathode voltage is positive, in detail later I will explain this operation also. Thyristor is under forward blocking mode. What exactly forward blocking, reverse blocking, all this we will see in the operation of thyristor. But here the concept concentrate on why it is called semi-controlled switch. Even though anode cathode voltage is positive, it will not conduct. When the thyristor will conduct? After giving the gate signal only, after giving the triggering pulse only. That means on is determined by control signal. When the firing signal is given to the thyristor starts the conduction. But when the thyristor will off, that depends on supply and load condition. That's why on is depends on control signal, that is gate signal, and off is depends on circuit conditions. That's why it is a semi-controlled switch or semi-controlled device. It may be semi-controlled switch or semi-controlled device. Here uncontrolled switch, or it may be device. Switch or device. Every device is used as a switch. That is the concept. Here semi-controlled switch or half controlled switch. A switch or device. Switch or device. Understood? That's why now you are done. What is semi-controlled switch or half controlled switch? On is depends on control signal, and off is depends on or determined by which one? Circuit condition. Here circuit conditions means both supply and load conditions. Depends on circuit conditions. Then what is the examples of semi-controlled switch? The example of semi-controlled switch is SCR, or it is also called thyristor. So many other semi-controlled devices also there. This is one example. SCR or thyristor is the semi-controlled device or half controlled device. Then third one is fully controlled device or switch. Fully controlled switch. Fully controlled switch. Or it may be a device. Both are on and off circuit conditions. Then what is that switch? Uncontrolled switch. On is control signal, off is circuit condition. Then what is that switch? Semi-controlled switch. Then how to define fully controlled switch? Both on and off is determined by or depends on control signal. Then it is called fully controlled switch. That is both on and off. Both on and off. On and off. Depends on control signal. Control signal. Then it is called fully controlled switch. Okay. Both on and off depends on control signal. Then what are the examples of fully controlled switch or fully controlled device? Examples. One is transistor family. The total transistor family is fully controlled. Transistor family means BJT, MOSFET, IGBT. This is fully controlled device. This is one example. The another example is GTO, gate turn-off thyristor, is also fully controlled device. For gate turn-off thyristor means we can turn on by positive gate signal and we can turn off by negative gate signal. On and off, both are control signal. Why the transistor family is fully controlled device? If you want to make turn on off BJT means for base we can apply positive signal. If you apply negative signal for base, then it can be turn off. That's why both on and off done by base signal. Even in MOSFET also, both on and off is done by gate signal. That's why this is treated as a fully controlled devices. Okay. This is the first classification of switches or devices. This is the first classification of switches or devices in power electronics. Uncontrolled, semi-controlled and fully controlled. This is first classification. Okay. Think. Or note down all these. Yes. You see the second classification of switches is the second classification. The second classification of switches in power electronics. The second classification, one is unipolarity and bipolarity switch. Bipolarity switch or device. Unipolarity or bipolarity switches are devices. It is not I am telling that unipolar, it is a unipolarity. Unipolarity in the sense it blocks only one polarity of supply. Only one polarity of supply. It blocks only one polarity of supply. That is either positive or negative voltage only it blocks. It cannot block both the voltages. One of the examples, so many examples are there. Later on I will give. Diode. Diode is the unipolarity device. Diode blocks only reverse voltage. Once the forward voltage is applied to the diode, it starts the conduction. It cannot block. Later on we will see. Later on I will give so many examples also. Then diode is a unipolarity device. That is what you mean by bipolarity switch. It blocks both the polarity of supplies. Both the polarity of supply. Okay. It blocks both the polarity of supply. Okay. Then what is the example? SCR. SCR blocks both forward voltage and reverse voltage. Okay. Later on we will see how it blocks both forward voltage and reverse voltage also. Next, unidirectional and bidirectional device. Unidirectional and bidirectional device or switch. Unidirectional or bidirectional devices are switches. Unidirectional means it conducts in one direction, only in one direction. Only in one direction. It conducts only in one direction. One of the example is SCR. So many examples are there. Bidirectional, it conducts both the directions. It conducts both the directions. It conducts both the directions. Then what are the examples of bidirectional device? This is triac and diac. Triac and diac is examples of bidirectional devices. Understood? This second classification. The third classification of devices. Third classification. The third classification of devices is, one is unipolar, not polarity I am taking, unipolar device or switches. That is, unipolar devices means conductivity is due to majority carriers. Conductivity is due to majority carriers. Then what is the example of unipolar device? MOSFET is unipolar device. Next, Schottky diode is also unipolar device. Schottky diode. Next, bipolar device. Bipolar device. That is, conductivity is due to both majority and minority. Both majority and minority. Both majority and minority carriers. Both majority and minority carriers. Okay. Then what are the examples? SCR, GTO, BJT, IGBT, all these are bipolar devices. Okay. This about what exactly unipolar devices and bipolar devices. What are the properties of these unipolar devices and bipolar devices? Later I will give. Then fourth classification of switches. Fourth classification is here composite switches. Composite switches. Composite switches. Here these switches are implemented to operate in multi-quadrants. Any device to operate in multi-quadrant, these composite switches are implemented. Then later I will give the examples of composite switches also. Okay. These are the different types of switches in power electronic circuits. In a chapter 1, in the concept point of view, this is one concept. Types of switches. Under types of switches, this is one concept. Okay. What exactly? General switches. What are the types of switches in power electronic circuits? Now I want to continue these concepts with respect to how to calculate switching losses in a practical switch, how to calculate conduction losses in a practical switch, then how to draw the characteristics, ideal characteristics of a various types of switches. All these concepts comes under types of switches only, chapter 1 only. This is one concept. Now we'll see the next concept is how to calculate the switching losses and conduction losses in a practical switch.